Okay, just going to add in a horizontal force as well, but to start with, we've got a box of mass 10 kilograms rests in limiting equilibrium on a rough plane inclined at 20 degrees to the horizontal, and we want to find mu. So if it's in limiting equilibrium, it's on the point of sliding, and the friction is at its maximum, and so the friction equals mu r. So force diagram, 20 degrees. So you could draw it as a box, but to be honest, we're not looking at centres of mass or anything like that. We're not going into that. So I would just keep all your models, personally, I just find it's easier just to keep it as a particle. And then the forces are just nice and clear with the angles. So you've got weight coming down, normal reaction, and the friction is stopping it from sliding down. And so the friction will be acting up this way, opposing motion. And then resolving perpendicular. So we've done one really similar to this already, actually. So this angle sitting in here is 20 degrees. Weight's on the hypotenuse, and so 10g cos 20 will give you the component of the weight perpendicular to the plane. So 10g cos 20 equals r, and r is equal to 92.0899. I would personally store that to x, and then resolving parallel, 10g sine of 20, so that's this little bit across here, so acting that way is going to equal F because it's in equilibrium, so there's no resultant force. Or you could do that as 10g sine 20 minus F equals 0. If there's no resultant force, it's stationary. If there's a resultant force, there'll be some acceleration, and then you would use F equals ma. So from there, you could write in F max if you quite like that. And so from there, F is equal to 33.51797. And F max is equal to mu r, and so F, sorry, we want to find mu, don't we? And so you can just do this one divided by this one is equal to mu, and mu comes out as 0.3639. I couldn't decide how heavily to round this. If you leave your answer to 2 sig fig, but I think in the next bit of the question, I would tend to maybe use it not quite so heavily rounded. But yeah, that's that bit there. So that's kind of should be quite straightforward. And then section B of this example, a horizontal force of magnitude P is applied to the box. It remains in equilibrium. What is the maximum value of P? So if it's in limiting equilibrium, you could put a force value this way, and that's going to start affecting the friction and the normal reaction. If you want the maximum value of P, you actually want this to be on the point of, sorry, so it was going like this, wasn't it? It was about to slide down this way, and we didn't have P in there. So it was about to slide down this way, and the friction was acting back. You could just push on it a little bit, and it will reduce the amount of friction by a little bit, and you won't be at maximum friction, but then you won't be at maximum P. So for maximum P, you actually want the box to be on the point of sliding up the plane, and in that case, the friction will be opposing that potential motion and acting down the plane. So we've gone from this being on the point of sliding down the plane to it being on the point of sliding up the plane, because that will maximise P. I don't like working with diagrams when they look like that. I don't know if Paul or someone might tell me off for this, but personally, I just would model the box as a particle because that's what we're doing. So just draw it as a particle. And then I like all my forces coming out, and I just find that much easier to work with. So P's acting in a horizontal direction, so P's coming out that way. R is perpendicular to the plane. If you're happy with this, go with it. Frictions, opposing motion. So it's coming down that way. So if P is big enough, it will be on the point of sliding up, not down. And then we've got weight acting down that way. So hopefully that's all right. And then you just do the normal thing, but you've just got, you know, this extra force to think about as well that's at a bit of an odd angle to the plane. But apart from that, life's good. So if that one is 20, this is a horizontal. And so this angle here is at 20 degrees. And then as per normal, you can draw in your right angle triangle there. And this angle here will be 20 degrees. Sorry, it's a bit hard to draw that. So same thing, there's no motion, so forces in equilibrium, resolving perpendicular to the plane. I've got acting this way, R, and that needs to equal anything acting down this way. So I have 10g cos 20 coming down here. But I also have a little bit of this one acting down in this direction, and that's equal to, so we've got right angle triangle, force on the hypotenuse, so that's equal to P sine 20. And so rearranging that, I'm expecting two simultaneous equations, so R minus P sine 20 equals 10g cos 20. And then resolving parallel, so anything going this way needs to equal anything going this way. So acting up the plane here, I've got P cos 20. That needs to equal F plus this bit here, which is acting in the opposite direction to P cos 20, and that is 10g sine of 20 to get to the opposite. So, and we know from part, we know that F is equal, sorry, I had to just think about that. We know that F is equal to mu r, and we have the value of mu from part A. So F will be equal to 0.364 r, because if it's on the point of sliding up, this friction here will be at a maximum. So F max is equal to 0.364 r. So substituting that into there, I get 0.364 r minus P cos 20 is equal to 10g sine 20. So two simultaneous equations. You can just put them into your calculator, so you can actually just put in like minus cos 20 as a coefficient of P, and then 10g sine 20. So you can literally put them in like that, so you don't have to faff about with decimals too much. And then from your calculator, P is equal to 82 newtons. But the point here is if P is at a maximum value, then the friction must also be at a maximum value too. So if you weren't pushing quite as hard on P, then yeah, it would reduce the amount of friction there. Right, I hope that made sense. If not, give me a shout, and I'd like to just do one or two a bit more similar to that one as well.